Okay, so now we'll introduce the notion of topological spaces, which provide the necessary structure to talk about notions of connectedness, um, continuity, and convergence. Okay, so these are topological spaces. All right, so we consider the notion of a topological space. Okay, which provides an analog of graphs in characterizing the notion of connectivity. Okay. All right. So as mentioned before, it also gives you a way of discussing sort of the most general space. It's like for discussing things like continuity convergence. And sort of the reason, of course, why that's important, as we sort of talked about earlier, was that one of the issues is like when one studies topological properties of spaces, right, is that we want to talk about things which are invariant under continuous maps. It's like with continuous inverses, right, which are homeomorphisms. All right, so let me now define it's like the notion of a topology. Right, so a topology on a point set, let's say X, right, is a collection big U of subsets of X, okay, and we call these subsets open sets. Okay, such that the following axioms hold. Okay. So the first of which is that X is open, okay, and the empty set empty set is also open. Okay. The second thing is that you can take open sets and you can take arbitrary finite intersections, and that thing would still be open. So the intersection of any finite collection of open sets is open. All right, and the reason why you want to allow only for finite intersections is because you might be familiar with the notion of topology. It's like which comes under real line. This idea of open sets, it's like under real line, and you probably realize that if you would take the intersection of open intervals, say from minus 1 over k to 1 over k, where k is an integer, and you were to take this union, it's like for all k, right? Then of course it's like the intersection of that would just leave the the point 0. It's like in that intersection, and so the point 0 on its own, it's not an open set in the usual topology on the real line, and so that's sort of an example of why it's like you might want to only consider it's like finite, it's like intersections. Okay. All right. And then the third thing is union of any collection. Okay, so this could be possibly infinite and possibly uncountable. Of open sets is again open. Okay, so these are sort of the axioms, it's like for a topology. Okay, and then if you have again a point set endowed, it's like with this collection of open sets U, we say that X comma U is a topological space. So then XU is a topological space. And oftentimes you omit the set of open sets U here. It's sort of implicit a lot of times, so we sometimes sort of omit sort of mentioning sort of U, and then just sort of by an abuse of notation, just say that X is a topological space. Again, with an understanding that when we say X is a topological space, there is an underlying topology which consists of this set of open sets which is attached to that. Okay, and we refer to X as a topological space. Okay. All right, so let's look at a few sort of extreme examples, if you will, of topologies. All right, and there are sort of two extreme cases, if you will. All right, so so we know that the smallest topology you can have, it's like on any point set X, right? It's the one where you have X in it and you have the empty set. Okay, so this is what is called the trivial topology. So the trivial topology. Okay, on a set X, right, is the one where you have U just being this set of X and the empty set itself. All right, and then there's the other extreme where basically any subset of X is an open set. Okay, and that's called the discrete topology. So the discrete topology on a set X, right, is this set of sets, right, A such that A is a subset of X, right? So any subset of X is in the topology, and we refer to this as the discrete topology. Okay, so let me also remark that it's like another way, there are many ways of thinking about topologies, it's like which are all sort of equivalent. Another way of thinking about topologies is instead of thinking about open sets, you can think about this idea of neighborhoods. Okay, so let me sort of remark that, and then maybe say a little bit about what neighborhoods are in that sense. So I'm going to write this at the bottom so I have more space for defining what a neighborhood is. So the remark is that right? The notion of open sets is closely related to the notion of neighborhoods. And it is possible sort of to define a topology in terms of neighborhoods and also in terms of closed sets instead of writing it in terms of open sets, right? There are sort of many equivalent ways of defining a topology. Okay, so I'm not going to talk about the case of closed sets. It's like that's something which is easy to do just by sort of the usual sort of idea that closed sets are complements of open sets. It's like, and then using the various properties of sets and their relationships, you know, between unions and intersections. It's like with sort of the unions and intersections of the complements, right? So so you can translate the axioms, it's like of a topology expressed in terms of open sets, it's like to sort of an equivalent notion of a topology expressed in terms of closed sets by just using those kind of constructions, again, applied to the axioms. So I'm not going to talk too much about the closed set stuff, but let me say a little bit about what happens in terms of neighborhoods. Okay. And just because it's like neighborhoods, of course, it's like our sort of an intuitive way of describing sort of, you know, things which are sort of close to each other in some sense, right? So, so definition, so that's what we sort of think about when we say neighborhood, is that, you know, there's a set of nearby points in some sense. So you might imagine that's the reason why it's closely related to the idea of connectivity, local connectivity, right? So anyway, so an open neighborhood of a point, so x in x, right, is an open set U in this topology, okay, such that x is in U, right? Sort of the obvious thing. It's so a neighborhood is basically just an open set. It's like a neighborhood of a point is an open set which contains that point. Okay, so so you can extend the idea of a neighborhood not just to a point but to a subset of x, right? So similarly, I should say open neighborhood, right? So for a subset A contained in X, right? U, okay, so I'm going to write little u. U contained in X is an open neighborhood of A, right? If U is open, right? Which of course just means that U is in my topology. All right, and this set A is contained in U. Okay, so that's obvious. That's an obvious generalization of the notion of an open neighborhood of a point to the notion of an open neighborhood of a set. Okay, so so these are again open neighborhoods. So let's now say something about neighborhoods, right? So a neighborhood of a point or subset, right, is a set containing some open set, or open neighborhood of the point or subset. Okay, all right. So so that's the idea of open neighborhoods, both of points and subsets, as well as the notion of a neighborhood. And as I said, it is possible to reformulate the axioms of a topology. It's like in terms of this notion of neighborhoods instead of dealing with open sets, right? But it's a little bit easier. It's like to work with open sets because there are fewer axioms it's like you have to deal with. Okay, so anyway, so that sort of is a brief introduction. It's like to the idea of the notion of a topology, which defines a topological space. And so let's just stop here for now.